You know when you see a screen just full of mathematical symbols? What's your gut reaction? For a lot of us, it's a little bit of fear, right? Like we're looking at some secret, impenetrable code. But what if we just flipped that idea on its head? What if we started seeing notation not as a barrier, but as one of the most powerful and honestly fascinating technologies humans have ever invented? It's a totally fair question, isn't it? Because it can absolutely feel that way. You see a symbol like sigma or that long S for an integral, and it feels like you're on the outside of some exclusive club. But is that really all they are? Just a way to make things complicated for no good reason? Well, the answer is a big, resounding no. And this is the core idea we're going to unpack today. Mathematical notation isn't just a fancy shorthand for writing things down. It is a technology that literally shapes how we think. It gives our minds new powers, letting us build ideas and see the world in ways that would be completely impossible without it. So how does this technology of thought actually work? Okay, first, let's look at notation as a kind of blueprint. It gives us the static structure, the architectural plans for building abstract concepts right from the ground up. And believe it or not, it all starts with something ridiculously simple, a pair of curly braces. This is set notation. With just these two little squiggles, we can start to organize the chaos of the universe into neat, manageable packages our brains can actually work with. And here's where the magic really happens. The exact same notation you'd use to group together milk, eggs, bread is also what mathematicians use to define 2, 4, 6, the infinite set of all even numbers. That incredible scalability, from the totally mundane to the truly profound, that's what makes notation a superpower for the mind. You can think of different notations as different kinds of blueprints. Over on the left, you've got algebra with its x's and y's. That gives us a grammar for talking about general rules and relationships. Then on the right, you have geometry, which gives us the symbols to lock down the pure logic of space. Each one is a specialized tool for building a completely different kind of idea. But hey, ideas aren't just static blueprints, are they? The universe is constantly moving, changing, and to get a handle on that, we need a way to think about change, about process. So let's move on to our second big idea, notation as a dynamic engine. So meet sigma. This symbol is basically an engine for adding things up, but in a very specific way. It's for when you're adding things in distinct countable steps. Like calculating your total profit by adding up January's profit, then February's, then March's, and so on. It's a step-by-step process, and this one symbol captures that whole idea perfectly. Now compare that with its cousin, the integral. This symbol does a similar job. It accumulates things, but it does it for stuff that changes continuously. Think about rainfall. You can't just add up individual drops, right? It flows. The integral is the amazing conceptual engine we invented to deal with that kind of smooth, unbroken change. And these engines can get super specialized. Isaac Newton, for example, he came up with his own notation, just a simple dot over a variable, specifically to think about physics. It was perfectly optimized to describe motion, velocity, and acceleration over time, an entire universe of dynamics, elegantly summed up with just a dot. Now, notation can even help us reason about what's good or bad in a computational sense. Take Big O notation from computer science. It's not just about whether a program works. It's about how well it works when you throw bigger and bigger problems at it. It's a language for a kind of computational ethics, a way to figure out what's going to scale gracefully and what's doomed to collapse. And this is exactly what that looks like in practice. Big O notation gives us an instant, high-level preview of an algorithm's future. Something that's O of log n, it scales beautifully. But an algorithm that's O of 2 to the n, well, that's going to collapse under its own weight. And it doesn't matter how powerful your computer is. This notation lets us see that future before we even start building. Okay, so we've got blueprints for structure and engines for change. For our third section, let's see how notation acts as a crucial bridge, connecting all these abstract ideas to the real, physical world we live in. Now, this might seem really basic, but I promise you it's profound. Unit notation, kilograms, meters, seconds, these are like little tags that anchor our numbers to reality. They prevent what's called semantic drift, which is just a fancy way of saying they stop our numbers from becoming meaningless and just floating away from the real world. I mean, just think about it. That tiny little m after the number isn't just a label. It's a piece of notation that fundamentally changes what 10 even is. It injects a pure abstract number with physical meaning. It connects the world of our thoughts to the world of actual stuff. And then there's what might be the most powerful bridge of them all, function notation, good ol' f of x. This is the engine of causality. It gives us a way to say, if you give me this input, x, I will give you this output, f of x. Seriously, every computer program, every scientific model, every economic forecast, it is all built on this fundamental bridge between an input and an output. So when you put it all together, you start to see it, right? These symbols aren't just a random collection of squiggles. They form a kind of alphabet of cognition. These are the basic characters that let us build and share incredibly complex ideas about how the world works. And this brings us to our final and biggest idea. If notation helps us build our thoughts, run our thoughts, and connect them to reality, well, then it's way more than just a tool. It's the very infrastructure of advanced intelligence itself. Let's just wrap this all up. Notation acts as our cognitive infrastructure in 4 really key ways. First, it's the architecture for our reasoning. Second, it's a form of cognitive compression, cramming huge ideas into tiny symbols. Third, it's the computational interface between our brains and our machines. And maybe the most mind-bending of all, it provides semantic governance, meaning the notation we have actually defines the kinds of ideas we are capable of having. Just let that sink in for a second. Notation is intelligence crystallized in symbol. All the struggle, all the breakthroughs, the genius of thousands of years of human thought, distilled, hardened, and captured in a simple mark you can write on a napkin. So this right here is the 3-step journey to insight that notation makes possible. It lets us take a messy, fleeting thought and give it a solid structure. Then we can perform computations on that structure, plan with it according to clear rules. And out of that process, something brand new emerges. A genuine insight we just couldn't have gotten to any other way. Which, of course, leaves us with one last, really fascinating question to chew on. If our current notations define the limits of our thinking today, what about the thoughts we can't even think yet? What complex, beautiful ideas about consciousness or society or the universe are just out there, waiting for someone to invent the right symbols to finally bring them to life?